I will be talking about new quantum error correcting codes that we constructed, in particular polytopological codes, inspired by the rich classification of Abelian anyon theories. This talk is based on two papers done in collaboration with Yuan, Arpit, Wilbur, Nat, who's in the audience, or maybe he left, and Dom, who might be in the audience. Let me start with some motivation, and then I'll tell you about what I'm going to tell you about. We all know that quantum error correcting codes are essential for building a reliable, i.e. fault-tolerant quantum computer. There are promising quantum error correcting codes such as the surface code and its variants, or bosonic quantum error correcting codes. But nonetheless, it's important to continue to develop quantum error correcting codes and search for new quantum error correcting codes so that we can further improve error thresholds, reduce computational overheads, and find codes that are, in general, better suited for current hardware. The goal of this work was to explore the space of quantum error correcting codes. Now that's a huge space, so we can start with codes that we know work well. So we know the toric code works well. The toric code belongs to a larger class of quantum error correcting codes called polytopological codes. So we explored the space of polytopological codes. Now I won't define polytopological codes precisely. I'll introduce them by way of example. But loosely speaking, polytopological codes are an amalgamation of Pauli codes, which includes both stabilizer codes and subsystem codes, and topological quantum codes. And what's nice is Pauli codes and topological codes make up for each other's deficits, and they have great benefits. Here's the plan for the rest of the talk. I'll start by introducing an example of a polytopological code, the toric code, it looks like. I'll then describe the anyon theory of the Z4 toric code. Anyon theories in general can be used to characterize polytopological codes. This is the quantized data that it will allow us to distinguish between polytopological codes and allow us to claim that we've constructed new polytopological codes. I'll then describe an example of a polytopological stabilizer code and an example of a polytopological subsystem code. I'll conclude by giving some advertisements and listing some potential directions for future work. As promised, the Z4 toric code. The Z4 toric code is defined on a square lattice with a four-dimensional qubit at each edge. The operator algebra of each four-dimensional qubit is generated by a generalized Pauli X operator and a generalized Pauli Z operator. These satisfy the relations shown on the far right. The stabilizer group of the Z4 toric code is generated by two types of stabilizers. There's a vertex stabilizer, which is a product of Pauli X operators around a vertex, and a plaquette stabilizer, which is a product of Pauli Z operators around a plaquette. And I claim, and you can check, that this is indeed an example of a polytopological code. One clear indication that this is an example of a polytopological code is that it exhibits an underlying anyon theory, which I'll show next. So now some more background. What is an anyon? Well, here an anyon for a stabilizer code corresponds to a violation of a stabilizer which can't be created or destroyed by a local operator. So let me demonstrate this with two examples. The first is an E anyon. This corresponds to a violation of a single vertex term. Now I can't violate a single vertex term with a local operator. But I can do this, at least in a local region, with a string of Pauli Z operators along a path in the lattice. This string operator, this string of Pauli Z operators, commutes with all the stabilizers along the length of the string, and only fails to commute with the vertex terms at the endpoints. So we refer to this as an E anyon. Similarly, there's an M anyon. This corresponds to a violation of a single plaquette stabilizer. Now, the types of anyons and their properties defines the anyon theory. There are 16 types of anyons in the Z4 toric code, these correspond to some composition of vertex violations and plaquette violations. So I've listed all 16 here. One is the special anyon. It's the trivial anyon. This one corresponds to violations of stabilizers that can be created by local operators. In general, these are just some composition of the E and M anyons that I showed on the previous slide. The next piece of data that we need to specify the anyon theory is something called the fusion rules. This is the group formed by composing violations. In the case of the Z4 toric code, the anyons form a Z4 cross Z4 group under fusion. And the last and most striking piece of data that I need to introduce are the exchange statistics. Anyons can exhibit exotic exchange statistics. E and M are somewhat boring. Those are both bosons. If I interchange two E or M anyons, the wave function is symmetric. More interestingly, if you take the composite EM anyon and exchange two of those, the wave function picks up a factor of I. We call this anyon a semion. We say it as semionic exchange statistics. So this is the anyon theory of the Z4 toric code. More generally, an anyon theory is defined by these three pieces of data. It's defined by the types of anyons, their fusion rules, and their exchange statistics. This is the quantized data that we'll use to characterize Pauli topological codes. It turns out this data is invariant under any finite depth or constant depth quantum circuit. Now, one can go through and solve, there are certain consistency conditions on this data. One can solve those consistency conditions to classify abelian anyon theories, and that's been done. We have a complete classification of abelian anyon theories. And there are many abelian anyon theories beyond those of the Z4 toric code or the usual Z2 toric code or even copies of the toric code. So that begs the question, for these more exotic abelian anyon theories, can we construct corresponding Pauli topological codes? And the answer to that rhetorical question is yes. And that's what we showed in our work. So let me illustrate this with two examples. I'll start by giving an example of a Pauli topological stabilizer code whose underlying abelian anyon theory is distinct from any toric code. This first example is the double semion stabilizer code. It's defined on a square lattice with four-dimensional qubits on each edge, just like the Z4 toric code. Here, the stabilizer group is a little more complicated. Now, don't worry about the precise structure of this stabilizer group. I'll explain where this comes from in just a moment. But it can be checked that these terms, these stabilizers, are indeed stabilizers. They're mutually commuting. And it can be further checked that this is a topological quantum code. One indication is that the dimension of the code space depends on the topology of the system. For example, if you put this stabilizer code on a torus, the code space has dimension 4. Now, in order to distinguish this from any toric code, we need to consider its anyon theory. There are two generators of the anyons of the double semion stabilizer code. The first I'll call B. B corresponds to a violation of a vertex term. This is the vertex term here. Now, I can't violate this vertex term with a local operator, but I can violate a single vertex term with a string of Pauli z-squared operators along a path in the lattice. This commutes with all the stabilizer generators along the length of the string and only fails to commute with the stabilizers at the endpoints. The other generator I'll refer to as S. S corresponds to a violation of both a vertex term and a plaquette term. And this is created by a string of Pauli X and Z operators. So together, these anyons generate all of the anyons in the double semion stabilizer code. It turns out there are 4 types. So we already know that this is distinct from the Z4 toric code. The Z4 toric code had 16 types of anyons. It turns out the usual toric code on qubits also has 4 anyon types. The fusion rules are also the same as the usual Z2 toric code. They form a Z2 cross Z2 group under fusion. But what's notable about the double semion stabilizer code is revealed when we consider the exchange statistics. B is a boson. It's boring. S is a semion. So if I exchange two of them, the wave function picks up a factor of I, and S bar, which is the composite of a B and an S, that's an anti-semion. The toric code on a system of qubits doesn't have any semionic anyons. So this is distinct from the toric code defined on qubits. It's also distinct from the Z4 toric code. It can be shown that this is distinct from any number of toric codes. So this is a topological stabilizer code which is new in the sense that it's characterized by a different anyon theory than that of any toric code. So how did we construct this model? We constructed this model by using the concept of condensation. In order to condense a boson, operationally what we do is we add string operators for that boson to the stabilizer group and remove any stabilizers that fail to commute with those string operators. Why should this be called condensation? Well, intuitively, those string operators create the bosons at their endpoints. But if we include this in the stabilizer group, now the code space is the +1 eigenspace of the string operator, and at least intuitively we can freely add and remove pairs of those bosons. And in that sense, those bosons have been condensed. So more explicitly, to construct the double semion stabilizer code, what we did is we condensed the E squared M squared boson of the, Z4 toric code. So we take the Z4 toric code stabilizer group and add to it string operators for the E squared M squared bosons. This can be done by just adding short string operators to the stabilizer group. These, it can be shown these create E squared M squared, pairs of E squared M squared string operators. These generate longer string operators. So if we add these string operators to the stabilizer group, we also have to remove any stabilizer that fails to commute. The vertex term and the plaquette term fail to commute with those short string operators. So we find new generators. These are products of the vertex term and the plaquette term, or just the square of the plaquette term. More generally, we can construct new polytopological stabilizer codes by taking a stack of toric codes and condensing bosons. This allows us to construct a large variety of polytopological stabilizer codes. They exhaust all modular abelian anyon theories with the Lagrangian subgroup. Now that contains some technical terms, but the point that I want to articulate is that they exhaust a large but restricted set of abelian anyon theories. So there are abelian anyon theories that aren't captured by polytopological stabilizer codes. So how do we capture the rest of those even more exotic abelian anyon theories? Like, what we can do is consider subsystem codes. So fortunately, Barbara gave a nice introduction to subsystem codes in one of the tutorials. So I skipped the introduction to subsystem codes. If you want to know more details, I'd be happy to discuss them afterwards. But I'm going to jump right into an example. This example we're referring to as the Z41 subsystem code because, as we'll see, it's characterized by something called the Z41 anyon theory. The Z41 subsystem code is defined on a square lattice with a 4-dimensional qubit at each site, and its gauge group is given by these two-body Pauli operators. And one can go through the calculations and see that this is indeed a topological quantum code. The logical subsystem has a dimension which depends on the topology of the system. So what are the anyons? In order to define anyons in subsystem codes, we need to change the definition slightly. Here, an anyon corresponds to a violation of gauge operators, which cannot be created by local operators. So in the Z41 subsystem code, here's the example. Here's the only generator, in fact. It's created by a string of Pauli X operators and Pauli Z operators. This commutes with all the gauge operators along the length of this string and only fails to commute with gauge operators at the endpoints. So what's the anyon theory of the Z41 subsystem code? Well, S is its only generator. So there are 4 types of anyons. Here, the fusion rules form the anyons form a Z4 group under fusion. S is a semion, S squared is a boson, and S cubed is, again, a semion. This turns out is different from any toric code or even any Pauli topological stabilizer code via our construction that I showed earlier. It's somewhat technical, but the reason for that is that S squared doesn't change the statistics of any other anyons when I fuse S squared to that anyon. I can fuse S squared to S, that creates S cubed, and it's still a semion. That property can't be realized by any Pauli topological stabilizer code. So how did we construct this? Well, here we use the notion of gauging out. It's analogous to condensation for stabilizer codes, but here we add string operators for the anyon that's going to be gauged out to the gauge group. Now, the gauge group can be non-abelian, so these string operators can fail to commute with one another. So we can gauge out anyons that aren't bosons. So how does this work? Well, take the Z4 toric code. In order to just to construct the Z4-1 subsystem code, we take the Z4 toric code stabilizer group, turn it into a gauge group by adding short string operators for E cubed M. So we gauge out the E cubed M anyon. This gauge group looks a little different than the gauge group that I showed on a previous slide, but we can find a simpler set of generators, which are all two-body. So more generally, we can construct new examples of Pauli topological subsystem codes by starting with a stack of toric codes and Pauli topological codes constructed through our condensation procedure and gauging out anyon types. This results in Pauli topological subsystem codes that are characterized by anyon theories beyond those of stabilizer codes. And in fact, they exhaust all Abelian anyon theories, even those that are non-modular or don't admit a Lagrangian subgroup. Let me conclude. Well, let me first summarize and say that, so at the end of the day, if you hand me an Abelian anyon theory, we can construct a corresponding Pauli topological code by taking a stack of toric codes and condensing and gauging out anyons. Now let me conclude with some advertisements and future directions. Is that the 2 minutes? So here are some advertisements. I think an important question moving forwards is assessing how useful these new examples are for quantum computation. So that's here. We found one example which I think is especially interesting. It's defined with Q-trits, but it has high bias noise error thresholds. It only involves two-body measurements. And there's a relatively simple way to insert twist defects. And you can do some logical operations with relatively low overheads. Another important question to ask is, are there any, so subsystem code, stabilizer codes correspond to a unique exactly solvable Hamiltonian. Subsystem codes, it turns out, correspond to a parameter space of Hamiltonians. So our Pauli topological subsystem codes define parameter spaces which you can explore. And one question is, can we probe these phase diagrams? Is there interesting physics hidden in these phase diagrams? And one thing that's interesting about our construction is we have a guarantee that in the gapped phases of the phase diagram, we'll find some of the Abelian anyon theories that characterize the Pauli topological subsystem code. And lastly, you can take our topological subsystem codes and turn them into Floquet codes. You can Floqueify them by scheduling the measurements appropriately. And maybe I'll conclude by just showing this slide. For potential future directions, everything we did was in 2 dimensions, but you could consider the characterization and classification of subsystem codes in 3 dimensions. I think it's also an interesting direction to ask whether we can find platforms which are amenable to simulating some of our models. Our models are relatively simple. They're all Pauli codes, so maybe these interactions are more natural to realize on a given platform. I'll stop here. Thanks.
Okay. Okay, thanks a lot. Andrew.
Hi, thank you for the nice talk. In ordinary surface code, excitations act like abelian anyons, as you noted, but twist defects act like non-abelian Ising anyons, or Majorana fermions, if you like. If you go to these other models where you have different abelian groups for the excitation anyons, do the twist defects still act like non-abelian Ising anyons, or do they act like more exotic kind of anyons?
Yeah, they act, well, I would call them non-abelian defects. But they do have properties that are similar to non-abelian anyons, and they do capture some of the physics that go beyond Ising non-abelian anyons. Like these in particular, these ones in this QIP2023 subsystem code correspond to like a Z3 parafermion topological order. Now I should note that none of these allow for non-Clifford, fault-tolerant non-Clifford operations. So all of the braiding and fusion that you can do with these twist defects still do logical operations within the Clifford group.
I see. And so there's a straightforward way to just calculate what the corresponding theory of the twists is?
Yeah.
Okay, thanks.
Thanks for the talk. It's very nice. So these constructions are all based on like these abelian models. Since these constructions are all based on abelian anyon models, are similar constructions possible for codes based on non-abelian models, such as on stringnet models, for example?
Yeah, that's possible. That's something that we haven't considered very deeply. So there are no-go theorems to say that we can't realize non-abelian anyons in polytopological codes. But you could ask, what's the simplest class of models, maybe stringnet models, that allow us to realize subsystem codes and, I don't know, simple enough stabilizer-ish codes that exhibit non-abelian anyons. And that I don't know. Yeah, but I think it's an interesting direction.
Yeah, to follow up, there's a way to generalize some features of the Pauli stabilizer formalism to quantum double type codes, right? And I guess one guess is that those types of X and Z operators can help do some of the non-abelian stuff. It would be fun for somebody to try to do that.
Great talk. My question was for identifying the platforms for simulating these types of physics. If you were to make a guess as to which platforms would be the best, or
yeah, that's a tough question.
Okay.
Yeah, so I don't think platforms, as far as I understand, have been really developed for QDITs, and most of the examples that are interesting and beyond Torah code that we have need to be are defined on systems of QDITs. Now you could use superconducting qubits and just use a third energy level, but I think there are issues there still that need to be resolved. You can use Rydberg atoms and there's a way to define QTRITs, but otherwise I don't know. I don't know that I'm able to make any predictions about the best platforms.
All right, thank you.
Yeah.
Oh, she was great.
Thank you very much for the talk. I have a question about the condensation process.
Yeah.
Firstly, when you mentioned about the string operators, could you explain what exactly they are? Are they stabilizer generators or they something else? And also, how do you realize the process of removing the stabilizers that fail to commute?
Yeah, I might have a good slide on this, but unfortunately everything is in a different language here. So this one's not useful. Right, so our construction involves turning those string operators, which aren't stabilizers, into stabilizers. And that's this process of condensation. Intuitively, you can think of this as measuring those Pauli operators, and measurements in the stabilizer formalism has that same effect. You add whatever Pauli operator you measure to the stabilizer group and remove all the stabilizers that fail to commute with that measured operator. And that's exactly what we're doing here.
And later on, you mentioned about this gauging out. Can I understand this condensation is actually just a gauge fixing process? It's the same as when we are So you start with a stabilizer generating set, a stabilizer generator, and then they do not commute. And then by doing some measurement, and then you create a new set of commuting stabilizer generators. Is this?
Yeah, that's an interesting way to think about condensation. I could have started with a gauge group that includes these stabilizers and these short string operators, and then gauge fixed to this particular stabilizer group. Yeah, I think that's an interesting perspective.
Thank you.
So this is pushing the last.
So much pressure. No. Yeah, thanks, Tyler, for the overview. Yeah, I have a question relating to the encoding of the logical qubit within different types of codes. Because in stabilizer codes, you have a large variety of ways to encode your qubit, like boundaries, internal punctures, twist defects. And for the subsystem codes, you only mentioned twist defects. Have you thought if there are any other types of encoding a qubit? Boundaries shouldn't be possible, but...
Well, so yeah, you could put in holes, but if you can put in holes, then it means it has a Lagrangian subgroup, and you might as well do that in a stabilizer code. So I think twist defects are most natural in the subsystem codes if you want it to be like a bona fide subsystem code. Alternatively, you can put this on a torus and encode quantum information, but otherwise, yeah, I haven't thought too much further than that.
All right. I think it's really a pity we didn't have any question to Floquet-fization. Let's thank our speaker for a nice talk.